And what I'd like to do now is walk you through a live demonstration of how it actually works. Now, for this, if you load the thing, you'll wake up to a blank landscape like that. You're just looking at blue sky and a piece of green earth. That's all you've got. Now, I'm going to start off with what I might call the foundation problem for SigmaPipe. And the foundation problem is what sparked the whole idea. It was when the high smelt plant was running in Kwinana, south of Perth. A problem that often occurred is young engineers would want to size a critical flow orifice plate. They'd say, look, I've got nitrogen at 12 bar pressure. The process operates at about 1 bar pressure. I need a critical flow orifice to give me 1,000 normal cubic meters an hour of nitrogen. I don't know how big that needs to be. Can you tell me how big we need to make the hole in the orifice? It's going to be critical flow. Now, of course, they could dig out the textbooks and code something in Excel, but they never had the time. They never wanted to do that. So they kept coming to ask me, and that's what sparked the whole idea for this thing. So what we'll do is we'll start off by doing exactly that. And then I'll extend it from there to show you how you drive the thing further. Now that little checkered flag up in the corner, that's the quick start. If you click on that, you get a menu that looks like this. And if you pass the cursor over these things, it'll basically highlight each one in turn. We're going to go with the most basic one, which is just a simple pipe with an orifice plate in the middle. And even though I've got a bunch of options here to change the pressure, the gas type, the pipe size, whatever, I'm not going to do any of that. I'm just going to say go. So what I've done is I've given you the wrong pipe with the wrong orifice in it deliberately because I want to show you how to change it. Okay. Now this thing, it's gone and solved it for whatever pressure it had. So if we say, okay, what is the pressure? It's running from 0.1 bar to ambient and it's temperature, blah, blah, blah. And there's a little window, a little orange icon up here. That's a pipe window. If you click on that, and you zoom into this thing, what you'll see is the size, it exposes the internals of the orifice so you can see how big it actually is. Now that orifice is going to be way too big for what we want, so let's make it a bit smaller. If I click edit and then I pick a number, let's say, I'm guessing, I don't know what size it has to be, let's say 10 millimeters, it has to be very small. This pipe's line is too big, this thing's DN200. That's not what I want. What I'd like to do is resize the line and set it to DN80 and keep it at schedule 40. So if I go and find that, so I've now resized the line to the size I want. Now the problem is I've got the wrong fluid conditions in here. So if I go and edit that, what it's telling me is it's 0.1 bar pressure. I don't want that. I want 12 bar pressure, so I can modify the fluid source. And the sink is not operating at 0. It's operating at 1 bar gauge, so I'll modify that. And if I then solve the model, what I can see is the flow is way too low. It's less than half what I want, so my 10 millimeter guess wasn't particularly good. So let's go and upgrade it a bit, and we'll just go in close. And let's have a guess at 15 millimeters and see what that looks like. So that's given me just over what I want, so I can make a slight adjustment to that, perhaps, and solve it again. And I've got something that's pretty much spot on what I wanted. So if I now look at what I've got in terms of, well, the pressure is very high. It starts at 12 bar and then goes down to 1 bar at the other end. But the interesting thing, of course, now is the Mach number, and that's telling me I've got a Mach number of 1 at the orifice, which is what I expect. Okay, and if I vary the downstream pressure, it's not going to do anything at all under those conditions. Now, let's assume that, okay, that problem's done. That's the foundation problem sorted. And it does demonstrate that for something like sizing a critical flow orifice, you can literally do that in about 1 minute. But let's say I wanted to add some extra stuff on the back end of that. How do I do that? All right, now here we just go with, I'm just going to copy this pipe section here. and then paste it downstream of the existing position and again. So I've just added some extra pipe bits on the back end, but I want to add a bend in. How do I do that? Right, well, here I've got an icon for existing and editing pipeline, and I just need to explain what this is. This is like a menu or a warehouse, if you like, of the standard piping bits that you might want to add. Now, if I edit a bend, and I can choose all kinds of different bends, if they're flared out or if they're long radius or short radius or whatever, but I say, look, that one's fine. I'm just going to go edit and update. Then I've actually got that one on the clipboard. So if I paste that downstream, there it is. I've got that bend in place. I can do the same thing again because I'd like to add a valve now. And on this menu, if I select a globe valve, same thing. I've now got that on the clipboard and I can paste it downstream. Okay. And if I then solve this, I've got no idea how the orifice and the valve are going to interact, so let's find out. What it's telling me is, okay, the pressure's distributed, dropping sharply at the valve as well. And in terms of Mach number, it looks like this orifice is controlling the flow, which is the same number it was before up there, and this thing is somewhat less than that. So if I set this at a different valve opening, let's take it down to 30% and see what happens. What we now find is that the Mach number is on the valve and the flow is less than the 1000. So we've shifted, the critical flow point has moved. But okay, let's not muck around with different valve positions. Let's map the whole range of valve positions to see what the actual installed characteristic of this valve looks like. So I can do that by clicking on valve curve here. And I've got a bunch of options. I can either do 5, 10 or 20 steps, but I know in this case that I want to do 20 to get reasonable resolution. I can space them evenly or bunch them at the beginning. I've got a feeling I need to bunch them at the beginning, so let's do that. And what it's going to do now is iteratively cycle through all 20 of those valve stem positions and calculate the flow at each point, and then give me the installed characteristic of the valve. So you can see it grinding through all those valve stem positions here. It's nearly done. There we go. So what it's telling me, this is the inherent characteristic of the valve, which of course is edited. You can go and drag the points around or modify them if you have a particular valve in mind. But it's telling me that under these conditions, when I hit 40% valve stem position, it's all over as far as the valve is concerned. It's only the orifice that's controlling the flow. Okay, so that's about as far as I wanted to go on the critical flow side of things. So now I'll change gears a little bit. I'll make the gas hot and low pressure, and then we'll see some of the thermal behavior of this thing. So the first thing is, if I edit the gas type and I say, no, look, I don't want 12 bar. Let's take it down to 0.2 bar, but 600 degrees in this case. And just for fun, let's add some water and carbon dioxide in at 10% each. So we're just making effectively a kind of flue gas. You can add whatever you want in there. So we've done that now, and I don't want this little pinhole in the orifice anymore. I need to open that up to get some decent flow through it because the pressures are much lower. So I'm just going to make that 70 millimeters. And I'm also going to open the valve up. I can just scroll on the mouse button to open the valve and then solve it and see what I get. And it's going to complain because I forgot something. What I forgot was that before I'd set the fluid sink pressure at 1 bar. Now I've got a 0.2 bar fluid source. It says, hang on, there's forward flow is not possible. What's going on here? So what we need to do is we need to edit the fluid sink and say it's ambient. Now it'll be happy. Now we can solve it. Right, so now what we've got, if we look at the temperature profile, it's dropping from 600 degrees to about 470. And if I look at this on the result graph, now this will show me along the flow path, I'm looking at how the pressure drops, but I want to also see how the temperature changes, and it's going down as you would expect under influence, just losing heat through the walls of the pipe to ambient all the time, as you would imagine it should do. Okay, now what I'd like to do is play some games with it, and the first thing is, let's add some insulation. Now, if I can edit any one of these pipes, and this small bar here is the lining and cladding activator. If I click on that, I get another menu opening up here, and if I choose to put a lining on there, cladding rather, I can decide how thick I want it to be and what the material is, and if I click whole line on that, then it's basically going to cover the whole pipe in 50 millimeters of external pipe cladding material. So I can solve that, and I'll see a somewhat different result. Now, I could make that pipe cladding semi-transparent just so I can see the pipe inside it. And if I now look at the temperature range, it's going to from 600 to 576. It's only lost 24 degrees, so it's been pretty well insulated. I can play some further games with that, and this little switch here allows me to switch the external stuff on and off and just see the pipe itself. But let's just go back to what it was originally and just verify that we've stripped all the lining off and it's giving me the same result it did before, which is the 130 odd degrees temperature drop. And let's go in the other direction now. Let's add external fins to the line, and if we make it the external pipe area effectively 20 times what the actual external pipe area is, it's only going to add fins to the straight pipes in this case. It's not going to do it to bends or valves. But then if I run the solution on that one, what I will find is that the temperature drop is now nearly 300 degrees. So again, as you would expect, it's just radiated a whole bunch more heat away to atmosphere. So if we then say, right, let's strip that away. So I'll get rid of all that. And now I'll do something a little bit different. Now I'm going to add external cooling water to the bulk of this pipe. And the way we do that is we add this box. Now we've got to figure out how big the box needs to be. We can play around with it. But what we're saying is this is containing cooling water at 30 degrees C, which is now your average. It's not doing countercurrent flow or anything. It's just defining an average condition outside the pipe, that the pipe will experience 30 degrees, a liquid velocity of 3 meters a second, so it's going to calculate a heat transfer coefficient from that. And of course, being a 3D object, we need to position the thing as we want it. And the rules around this say that only straight pipes are allowed to cut the walls of such a box, because what the simulator is going to do is it's going to snip the pipe into 2 bits and calculate them separately, so it needs to know where they're being cut. But if I solve that, it should then tell me that I'm sucking even more heat out, and I'm dropping it to nearly 200 degrees. And then if you look at the pipe wall temperature, for example, you can see that it's very cold where the water is, and it's quite hot at the bits that are not water cooled. All very much as you would expect. So if I then get rid of that and just solve it again, it's just going to go back to what I had before. Now, there's another feature that's worth noting on this thing, which is if you look at, sorry, just let me close those up again. If you look at the end of this pipe, there's some switches here. It says ambient temperature and process temperature. Now, we know with this hot gas, when it goes into the pipe's actually going to grow according to its own thermal expansion material property. So that pipe should actually move when it gets hot. So if I click on process temperature, you see how that moved and back again. And if I want to quantify that, what I can do is I can set, I can use 2 sets of axes and measure the distance between them. So I can set one of them on the end of that pipe, move it, and then put the secondary axis basically on the same thing, and it tells me right up there, it says those two are 33 millimeters apart. So because it's in two axes, it's roughly 20 millimeters along each line, that the pipe has physically grown under the influence of the temperature that is picked up from the process gas. If I want to, I can define fixed points and linear compensators and come up with some estimate of what kind of compensation is needed to accommodate that expansion if I need to. One of the worked examples does that. I don't propose to go into that here. Okay, now the other thing I'd like to illustrate is what happens when you muck around with materials. So let's just say, for argument's sake, I decide that that first pipe section needs to be copper, and I run it again and see what happens. Well, the solution tells me that there's something weird going on there because that copper looks like it's all mucked up somehow. And if I right-click on that and interrogate the properties, it tells me the average wall temperature is 482 degrees. Okay, so let's go and look in the materials editor, which is this little icon up here. And if I pull up copper, what this is telling me is that by the time copper hits about 350 degrees, it doesn't have any strength left. It's basically turning to plasticine, and it's not going to maintain. The integrity of that pipe is compromised, basically. That's why it had that funny look about it. So if I then say, okay, let's knee-jerk and go in a different direction, instead of using copper, we'll actually use Inconel, which is going to be strong up to very high temperatures. And, well, of course, with Inconel, no problem. It's only going to be a small percentage of its yield strength. It's only 2.8% of its maximum yield strength. So the thing about this is when you define a material, you are defining its temperature strength characteristic. And the model is calculating, when it normally solves, how much wall stress have you generated and is the integrity of that pipe okay or not. And in fact, right down the bottom here, there is you can just click on that and use the color scale for pipe integrity as well, whether it's busted or not, which it isn't in this case. Right, now that's the thermal expansion part, or the thermal effects I wanted to demonstrate. I've got one more aspect I would like to demonstrate, and I hope that you guys aren't too fatigued with this yet, but let's keep moving anyway. Firstly, I clear the landscape, and I'm going to pull up one of the other quick starts, which is this thing called a long pump and long pipe. So what that is, it's a pipe going 100 meters off in one direction, then coming back, then going up a bit, and then ending in a fluid sink. And that's all calculated and solved. But the thing I wanted to show you was, if I look at the pump curve, it's basically given me a default pump with pump characteristics that may or may not be what you're interested in. You can edit them, of course. But it's saying everything's healthy, that's a good solution. Now, let's perturb the system a bit by looking at this is a water tank, and instead of putting the water in at 40 degrees, let's put it in at 90 degrees. So I'm getting a little bit close to boiling. The vapor pressure of the water is going up a bit, and the model's complaining. It says something there about surge, no, cavitation. So if I look at the vapor fraction, that's basically telling me that around the pump there's a little bit of vapor appearing in there. There's something going on there. And if I look at the pump curve again, it tells me the pump is cavitating, not happy. Need to do something about it. Now, there's several things we could do about it, but let's say, for argument's sake, in this case I've said the net positive suction head is 5 meters. Now, let's say it was actually 4 meters, not 5 meters, and of course that's related to the pump manufacturer, and it's the shear between the impeller and the maximum speed. So if it was a lowest speed machine, maybe a bigger impeller, I don't know, and we just put that to 4 meters and resolved it, that in fact does take the problem away and everything's happy again. All right, so you can deal with pumping quite easily there. Now, I'm just going to edit this a little bit because I don't want these pipes to be all that long. So I'll just turn these 200 metre lines into 2 metre lines, and that one as well. I'll just make it a 2 metre line. And what I'd like to do now is just show you a slightly different way of editing, which is in fact, it's a more flexible way of editing to get what you want. If you open this line editor, now we need to use this, this semi-transparent thing, because if it's like that, now if you're working on a laptop with a relatively small screen, it's a problem because this thing's in the way and you can't see the pipe underneath it. But if you click on that button, it'll make it semi-transparent. You can still do everything with this, but you can still see the result underneath. Now the first thing we want to do is want to click on this button. I'll just make it clear so you can see what it is. That's going to remove whatever the last bit of the pipe is. So if I do that, I remove the last bit. Now I've got a green button here. It says, okay, I can add another pipe section if you want. That's how you grow a pipeline. But let's say I don't actually want to put a straight pipe on. I want to put a cone in there. I want to make it bigger. So I want to go from schedule DN200 to DN450 over a 500 millimeter cone piece. I'll make that transparent again, and there you can see the cone piece that's in place. If I then create a new pipe section, you can, you're now growing a bigger line. And now what I want to do is put a heat exchanger tube bundle in there. I want one that looks like that. And I want it to be 8 meters long. And now I can add the tube bundle. And I can add another pipe section and add a fluid sink. And now I've just gone and built something different there. If I solve that, it's now going to tell me that, yep, okay, you can get a nice healthy flow through there. If I look at the pump curve on what that looks like, it's actually, there's not a lot of flow resistance actually. That pump is running at low pressure, high volume, well away from its optimum design point. But that's not really what I wanted to do. What I wanted to do was actually vaporize that water, turn it into steam. So what I need to do now is I need to add a steam enclosure to that heat exchanger, which I've just done. And if you say, well, what steam conditions did you just add? The way we interrogate that is we turn the pipes off, which means we can now edit this thing and have a look at it. It's 20 bar steam. I can change that to whatever I want, but it's saturated steam, so it's just the one number I need to put in there. Alright, so let's turn the pipes back on and solve it and see what happens. And what I find is it's grizzling about something else. And the something else that it's grizzling about is when I had those 100 meter pipes, what I didn't want to do is calculate on a very short pipe diameter basis, because it had a long way to go with all those long pipes. So it was actually calculating on 100 diameter cuts all the way along that long pipe, and I never changed it. What it's warning me about is it's saying, hang on, you've got a phase change going on, and you've got a very long diameter calculation. You've got to be careful with phase changes. You need to bring it back, because you can miss important information if you set it that way. So I've deliberately set it up to be a problem, and what we then need to do is we can go to edit the solver resolutions. There's the 100 meters. We don't want that, so let's come down to 3 pipe diameters and solve it on that, and that should make it happy then. So this thing, incidentally, is supposed to be like a traffic light. If it's red, the error's still big and you've still got a way to go. As it turns to a more orange color, that's more like the amber light, and when it gets to green, then that's close to being solved. So that's doing fine. It has solved. Let's look at the flow regime to start with. Now what I'll do is I'll turn off that actual steam jacket so that you can see more clearly what that looks like. And what we're getting is you've got liquid coming in here, then it looks like it's passing through wavy or stratified horizontal. It's then moving briefly to slug flow, and then it's going to annular mist for a big part of it, and then it turns to gas flow for the final bit and rushes out. If we look at the pump to see how that's doing under these conditions. What we find is that the pump is facing a significantly higher back pressure because doing all this vaporizing and thrusting all the steam through is actually making it work quite hard in that sense. And if you can also see that on the pressure drop here, you can see that most of the pressure drop is in fact across these tubes where the phase change is taking place. If you look at temperatures, what you find is an interesting thing. The temperatures are picking up as you go through here, but you reach a peak at the outlet of the heat exchanger and then it drops down again. Now, why on earth would it do that? The answer is partly to do with gas velocity. If you look at what the gas velocities are doing, you see that all that steam in this DN 450 line, that's running at 330 something meters a second. It is ripping through there really, really fast. Is that close to sonic or supersonic? Well, if we look at the Mach number, no, 0.67, it's still subsonic, but it's running pretty darn quickly. So if you then ask yourself the question, well, okay, what exactly is the speed of sound in steam under those conditions? Okay, there's an easy way to do that. There's a utility here called thermotransport properties, and if we bring that up, we can select whatever fluid we want here, all of them are there, and then you can set some logical ranges for temperature and pressure that you want to interrogate, and then tell it to go and fetch the data. So all I've done here is I've set it up so that it jumps in 10-degree increments, and it's liquid at 90 degrees, and it runs all the way through. Now, this outlet of the heat exchanger, where it's that, at that point it's about 170 degrees, then it drops to about 140 in the pipe. And that's obviously just the kinetic energy. It's just transforming, it's playing around with thermal and kinetic energy. But you can see that the speed of sound here is approximately 500 to 516 or something. That's the range you're talking about. And if you wanted to dump this into Excel, you just copy to the clipboard. Let's do it just for the heck of it, just to demonstrate. And I'll drop that into Excel. So if you need to go and do something else with that data, or if you need to know the thermal conductivity of something or whatever, you can. That's really, really easy to play with. But the final thing I'll do here is just to, oops, no, that's not the one I wanted, is just to demonstrate a sort of an independent check on what this model is trying to tell us, is that we've got 115 tons an hour of water going through there, turning into steam. It's chewing up about 78 megawatts of energy. Let's just do a quick independent calculation. Does that make sense? That much water turning to steam under those conditions. And there's a utility here that's very easy to use for that. We're going from 90 degrees to 170 before the acceleration into that pipe. And we're telling it that it's using 78,400 kilowatts. And it calculates 116 tons an hour, which is very close to that number. Of course, this is a simple thermodynamic calculation without taking any kinetic energy effects into account, but it's approximately correct. So it tells you that the thing is, it's inherently telling you the right story. So that's as far as I wanted to go with demonstrating how this thing works. If you're interested to play with it, I would recommend replay the video and follow what I clicked on to make all these things happen. And the other thing I'd like to mention is that there is no implication anywhere that this piece of software is perfect. It will at times do things it's not supposed to do, like everything else. But what I will tell you is, if it does misbehave and you tell us about it, we'll fix it. So I'll leave it there and I'll take any questions you might have. Thank you.